I will share my screen. Okay, so good afternoon, friends. Uh, Sorry, good morning, friends. Now we will be today going through the timing diagram of 8085. Now, what is the timing diagram for 8085 implies that how our microprocessor 8085 is going to work by using these timing diagrams. Actually, what you understand by a timing diagram is we have studied last year that how we are going to generate the clock pulses, right? So clock pulses are actually the square wave pulses that we have tried to generate by using crystal oscillator. So as I told you earlier that this crystal oscillator is of 6.14 megahertz, and this is going to provide the 8085 with a clock pulse of say uh, okay say 3.3 megahertz. So what happens that on each of the clock pulses the microprocessor is supposed to do certain works, and that is called as the timing diagram. So we are concerned with how this microprocessor is going to work with using this timing diagram. So this is what we have to study today in our today's class. So the first one is, what are the timing diagrams? The 8085 microprocessor has 7 basic machine cycles. Machine cycles, remember this, huh? So these machine cycles, they are opcode phase. The first, what microprocessor is going to do is, it is going to fetch the opcode from the program where we have written the program. Say we have written that program from 6000. So it is going to fetch the opcode first, then it will require, say, for to fetch a cycle it will require 4 t states or 6 t states, means cycles, 6 clock pulses or 4 clock pulses it will require to fetch that opcode. Then it requires, say, the machine cycles requires to read the memory. So to read memory we require the cycle, say, around 3 clock pulses. Memory write cycle also requires 3 clock pulses. Input output read cycles 3 clock pulses. Input output write cycle 3 clock pulses. Interrupt acknowledge, whenever there is an interrupt from other peripheral devices, then the 8085 is supposed to give the acknowledgement that the microprocessor has received the interrupt call. So that is the clock pulses which are required is from 6 clock pulses to say 12 t pulses, and bus in ideal cycles. So these are some of the cycles that are required by this 8085. Now we'll look at them for one by one. So the timing diagram is a graphical representation. It represents the execution time taken by each instruction. Timing diagram, remember this. So timing diagram is actually a graphical representation that we have earlier studied, that how square wave pulses are being drawn, and according to that square wave pulses, how the program, how the device works. Means we have studied, say, like the timing diagram of say the counter, or say a shift register. So for each and every clock pulse the register shifts the data from left to right or right to left accordingly, or the counter counts the signal. So accordingly we have the timing diagram. The same timing diagram we are trying to use over here in the 8085 microprocessor. So it represents the execution, actually the execution time taken by each instruction in a graphical format. So we are going to study this. We are going to see this cycles also and the timing diagrams also. The execution time is represented in t states. Now it is being represented by t states. We call it as a timing states. So each clock pulse and the time, the total time which is required to execute a particular instruction, we will call that as a t state. So that is there. Now the second one, okay, control signals. Now these control signals, you remember the block timing and control unit. This timing and control unit generates this control signals. Accordingly it uses those control signals to say uh, to conduct different operations. So these are being given over here. I have told you input output oblique memory bar. So and the status line S1 and S2, and accordingly the data bus status are being varied. So this is over there. So when we have this input output memory bar as 0, S1 S2 as 0, the data bus status, the data bus stops working, so it halts. When it is 001, the memory is written, the data is written in the memory. When it is 010, then the data from the memory is being read. When it is 101, then we are having the input output write, means that input output devices are written. When we are having 110, input output read, so the data is being read from the input output devices. 011, the opcode is fetched from the memory location, so that is the status control signal. And lastly 111, it means that there is an interrupt, and the interrupt is being acknowledged by the 8085 microprocessor. This is the control signal. So you remember this input output memory bar, that there was a signal, and the status signal, that is S1 and S2. Actually they were S0 and S1. Here it is by mistake it is written as S1 and S2. They are S0 and S1. So depending on the combination of these three, different sorts of signals are being provided to data bus, and accordingly the data bus uses those signals to write, to read in the memory, to write in the memory, or to read from the memory, likewise, or to halt, or to give the interrupt acknowledge. So these are some of the signals which are being particularly used by 8085 to generate the control signal. So this was there. Then what are machine cycles? Now these are some small definitions of the cycles or the clock pulses which are required to operate the opcodes. So the time required to access the memory or input output device is called as machine cycle, right? So remember this small definition: the time required to access the memory or input output devices, means the clock pulses which are required to access the memory, to give the data or to read the data from the memory, or to read the data from the input output devices. The time which is being required is the total time, the total number of clock pulses is called as the machine cycle, right? So this was the definition. Then we are having T states. So T state, the machine cycle plus the instruction, means the total time which is required to execute a particular instruction is called as a T state. So it is the combination of the machine cycle as well as the instruction cycles, and it takes multiple clock periods. So multiple clock timings are being required. So if you are able to see the diagram over here, it is graphically shown that what is the rising edge and what is the falling edge. You know that a negative edge and the positive edge. So positive edge goes from low to high, and the negative edge goes from say from high to low. Accordingly, the status is over there. So we call this as a rising edge or a positive edge, and the second one is the falling edge or a negative edge. Now on each of the falling edge or the negative going edge, the microprocessor is going to perform one particular function. So these are the cycles that we are going, and we calculate or we count a cycle from say the negative edge to the next higher edge, the positive edge. So we will be calculating that, and that is called as the 1T state over there. So this is that, and the time period, you know that the time period is calculated by 1 by frequency. So the frequency, which is the internal clock of the microprocessor, which is generated by the crystal, and it is around 3.3 megahertz. So this is over there. Then we are having machine cycles of 8085. So 8085 microprocessor has 5 basic machine cycles. They are the opcode phase cycle, that is 4T. Memory read cycle requires 3T, T states. Memory write cycle requires 3 states. Input output read cycle requires again 3 states, and input output write cycle requires again 3 states. So these are those machine cycles which are being used by the microprocessor 8085 to execute the opcode, or to read in the memory, to write in the memory, or to write in the input output devices, or to read from the input output devices. So these are called as the machine cycles. We'll go one by one over here. So the machine cycles of 8085, the processor takes a definite time to execute the machine cycles. Now, the time taken by the processor to execute a machine cycle is expressed in t states, small t states, right? The time taken by the processor to execute a machine cycle is expressed in t states, 1, 2, 3, 4, right? According, one t state is equal to the time period of internal clock signal of the processor. Yeah, we have seen that in the earlier slide over there. So the t state starts from the falling edge of a clock pulse. It starts from that and to the next higher edge. So it goes like this. So that is there. Then opcode phase. Now this is the real diagram where we are able to understand what actually is happening when we are saying that we are going to fetch a opcode from the memory location, and what are the actual happenings over there. So these are shown by this T1, T2, T3 and T4 states. So these are the clock pulses over there. And accordingly, what will be the positions of the address bus, that is for the higher order address bus, that is A8 to A15, then the lower order address and data bus, that is AD0 from AD7. So this is how it's going to work. Then what is the position of address latch enable over here? Then what is the situation of input output memory bar and S1 and S0 signal? So that uh, the table that I have shown you earlier, which was showing you all the possible conditions or probabilities of, say, the input output oblique memory bar, S0 and S1, and accordingly the data bus is going to work. So that was the timing diagram of the control signals generated by the timing and control unit. So that is being used. So over here now, what actually opcode fetch machine cycle means? So whenever we are having a clock signal of t state, so this is the one T1 state, then T2 state, T3 states and T4 state. Simultaneously, we are going to see what happens in a particular t state. So in the first timing cycle, what happens is the higher order memory location, memory address line A8 to A15 will become high. Then AD0 to AD7 will also become high, so that it will give you the memory location, address of the memory location where the opcode is being written by you. So that is there. So in the T1 state, this will be happen, and address latch enable will be high, which implies that the address, lower address line, lower 8-bit line will be using it as a address line. So we are going to use that over here. So now the address is being given to the memory location. Then input output memory bar S1, S2, this status line will be given as, so if you are able to see here, it's low, then read. So we have to read. So in that first T1 cycle, the read terminal is high, which implies that read is not going to perform right now. So read is going to perform in the second timing cycle clock pulse, that is T2. So if you are able to see over here now, what happens in T2, the lower order memory address bus is being now broken, and now this data line, this lines, 8 lines are being used for to transfer the data. So this is over there. Now this has used for opcode, and if you are able to see over here, address latch enable is now low, which implies that address is latched now. The data, these 8 data lines are being used over there to transfer the data. So it is going to use. Now in the last column, if you are able to see, that is read bar, that signal is now low, which implies that it is going to read the opcode from that particular memory location. So it is going to read that opcode in the second clock pulse. Now when the third clock pulse goes, the opcode is being given on the data bus like this, and the data is being transferred to the microprocessor for further processing. So during this time, the read terminal will remain low over here. Sorry. So, and then as soon as this T3 is being executed, T3 is gone, the third clock pulse, this will again be shifted to address latch enable. So this is over there. So sometimes it requires T4, but maximum times to fetch the opcode from the memory location to the microprocessor, it requires only 3 three clock pulses over there. So this has been shown by this clock timing diagram, and this we call it as machine cycle of 8085, which is used to fetch the opcode from the memory location address specified in the program. So this is over there. So I hope you understood that. I will again repeat it for you. If you are able to see, this is a timing diagram for the opcode to be fetched from the microprocessor. For example, we have studied, like we were working on that. The first instruction was MVI A03, if you remember that. The opcode was 3E and the data was 03, right? So what we are trying to, what I'm trying to tell you here is the 3, which is an opcode which is written in the memory location 600, is being fetched, is being taken from that memory location to the microprocessor and to the instruction register to decode that and to execute that and to generate certain type of clock signals for execution, right? So for the first instance, what we require to fetch that opcode, that is 3E, from 600 to the microprocessor or to the instruction register to decode it for decoding purpose. So that particular time lag is called as a machine cycle, right? So this is over there, and I will again repeat it for you. So in the first column, if we are able to see that there are T1, T2, T3 and T4 pulses. We are working on to fetch the opcode from that memory location and to put it in the microprocessor or to the instruction register, right? So that is over there. Here it is going to show you the status of the higher order address bus, that is A8 to A15, and the lower address data bus, that is AD0 to AD7, because the same line is going to be used for the address as well as for data. Therefore it is being multiplexed. So sometimes it is going to be used as a address line and sometimes it is going to be used as a data line. So that is over there. Then this is the address latch enable, which is going to control that latch for whether that is being used for address or whether it is being used for the data. So that is being used over here. And this is the status signal, input output memory bar, S1 and S0. So those signals are being used to control the data bus, which I have shown you earlier. So this is over there. And the last one is, the last column is to read the data from the memory location. So that is the signal over there. So these signals are being controlled by using these clock pulses. During the first clock pulse, as you are able to see, the higher order address bus is being active and the lower order address bus is also active. That is, the address of the memory location is being transferred in the first memory location. Address latch enable is high. Input output memory and S1 S0 are shown over here like this. And then the read signal, that is read bar, it is high now, so we are not going to read in the first clock pulse, right? So we are going to read it in the second clock pulse, that is T2. So T2 is over there. In T2, what happens? AD0, as soon as the address latch enable goes low, the address line, the lower order address line, now is being shifted to data line. Now the data is being read. So data, that is the opcode, is being given to there, and now then only the read signal will go low, which implies that we have to read the data from the memory location specified by the address, and the data is being put on the address bus. So this is being put over here, and when it is say input output memory bar is 0, S1 is 1 and S0 is 1, the data is put on the data is read from the memory to the microprocessor. This is the whole signal which is going to perform in each and every opcode to be fetched from the program which we are trying to write on that. So this is over there. Then similarly, for the next opcode fetch machine cycle, I have told you this. So for this, each instruction of the processor has 1 byte opcode. 1 byte opcode रहता है हमारा. जैसे हमने लिखा है MVIA 03, तो 3E is the opcode. Even when I have written LXIH, which implies that only 21 is the opcode and the rest one is the data. So 21 is the opcode over there. So only one opcode is there, and to fetch that particular opcode from the memory location where we have written program to the microprocessor or to the instruction register, we require these 3 clock pulses or T states. So these are there. So each instruction of the processor has 1 byte opcode. The opcodes are stored in the memory. So the processor executes the opcode fetch machine cycle to fetch the opcode from the memory. Hence, every instruction, all the instructions starts with the opcode fetch machine cycle, right? सबके लिए machine cycle की ही जरूरत पड़ती है, और उसके लिए सबसे पहले ये तीन स्टेट्स यूज होते हैं. उसके बाद इंस्ट्रक्शन रजिस्टर जब उसको डिकोड करता है, उसके बाद एक पर्टिकुलर ऑपरेशन एग्जीक्यूट होता है. Now, the time taken by the processor to execute the opcode fetch cycle is 4t, right? 4t. So 3t में तो पूरा का पूरा काम हो जाता है. लास्ट वाला एक t स्टेट्स हमारे उसके लिए जो डेटा इंस्ट्रक्शन रजिस्टर में जाके डिकोड करता है, उसके लिए हम लोग उसको यूज करते हैं. तो अगर हम लोग यहाँ पर देखें, जो ये 4th साइकिल है, इसमें एक्चुअली वो जो इंस्ट्रक्शन है वो डिकोड हो जाता है. So that is why we call this as we require 4 cycles for the opcode to be fetched. So that is over there. Ab in this time, the first T states are used for fetching the opcode from the memory, and the remaining T states are used for internal operations by the processor. That is to decode the opcode, right, and to generate the instruction. So this is how the opcode fetch machine cycle is being used. So this is over there. I hope you have got this, and we'll come to the next part in the next class. Today it's enough. I hope I will again repeat for you. So this was we were studying timing diagram of 8085 microprocessor. 8085 microprocessor. In that, what we have studied is what are the timing diagrams which are required, essential for 8085. Now the 8085 microprocessor has 7 basic machine cycles. They are opcode fetch cycle, which requires 4 T states or 6 T states depending on the fetch. Then memory read cycle, that is 3 states. Memory write cycle again requires 3 states. Input output read cycle, it requires 3 states. Interrupt acknowledge cycles, 6 T states or 12 T states, and bus idle cycles. So these are over there. These are some of the timing diagrams. Then what are timing diagrams? They are actually the graphical representations of the clock pulses. It represents the execution time taken by each instruction in a graphical format. We are going to learn that. The execution time is represented in T states, 1, 2, 3, 4, T1, T2, T3, T4, T states. So this is how it is being represented. Then this is the control signal which is being used for the data bus status. So we are having three signals. These are input, output, memory bar, active, low, S1, S0 and S1. So these are over there. Data bus status output, what will be the output? So when all the 3 combinations are 0, 0, the data bus will be halt. When it is 0, 0, 0, 1, 0, 0, 1, then it is going to write in the memory. When it is 0, 1, 0, it is going to read from the memory. When it is 1, 0, 1, it is going to write from the input output devices. When it is 1, 1, 0, it will read the input output devices. And 0, 1, 1, I have shown you 0, 1, 1 is for opcode fetch. For that we require this. So the status control signal, that is input output, memory bar, S0 and S1, should be 011 to fetch the opcode from the memory location. And when all are 1, that is 111, we have to generate the interrupt acknowledge. So this was there. Then instruction, what is the instruction cycle? The time required to execute an instruction is called as the instruction cycle. Then we have a machine cycle. The time required to access the memory or input output devices is called as the machine cycle. Okay, I'm sorry, hold it for a second. I should close this. Yes. So the time required to access the memory or input output devices is called machine cycle. Then we are having T states. I've shown you T states. What are? One clock pulse, one square wave is called as clock pulses. So the machine cycle and instruction cycle takes multiple clock periods. A portion of an operation carried out in one system clock period is called as a T state. I have shown you T equal to 1 by F. That is actually the frequency which is generated, which is given by the internal clock or the crystal, that is around 3.3 megahertz. So that is over there. This is how we are having the rising edge or the positive edge, which is going from the lower voltage to a higher voltage, and we call it as a rising edge or a positive edge. Second one is the falling edge, higher to lower and high voltage to low voltage. That is what we call it as. It works on the falling edge. So this is over there. So these are called as T states. So machine cycles of 8085 are opcode fetch cycle, that is 4T. Memory read cycle, that is 3T. Memory write cycle, that is 3T again. 3 timing clock pulses. Input output read cycle, 3. Machine cycles, the processor takes a definite time to execute the machine cycle. The time taken by the processor to execute a machine cycle is expressed in T states, right? We have shown that. Then this is how the opcode fetch is done by the machine cycles. This is what I have shown you. It requires T1, T2, T3, and T4 for the opcode to be fetched from the memory location to the microprocessor unit. So these are over there. This is what we have studied, and in that what we have studied, each instruction of the processor has 1 byte opcode, right? The opcodes are stored in memory, so the processor executes the opcode fetch machine cycle to fetch the opcode from the memory. Hence, every instruction starts with opcode fetch machine cycle, right? This is what we have studied. The time taken by the processor to execute the opcode fetch cycle is 4 timing clock pulses. And in this time, 3T is used to fetch the opcode and 1T is used for the processing or for the decoding of that. So this was what we have studied over there. Thank you very much. If you have any queries, you can ask me on the WhatsApp group or there. Okay,
Yes,
thank
sir.
you very much. Thank you for listening. I hope you have got, and I hope that you will follow my YouTube videos and you also like those videos, right? Thank you very much. Have a nice time. Stay safe. Stay home. Have a great day. Good day. Bye.